everybody, I am Dr. Punyadarshini Poonam Tripathi from Agricultural and Food Engineering Department, IIT Kharagpur. In the course Advances in Agricultural Engineering, I will be presenting the module 2, and before that I will like to tell about the references that I have used for this module, some books that I have enlisted here as well as the journals. Now coming to this module 1.2, this is basically exploring solar energy for food processing and preservation, because in the previous module we have seen module 1.1 the use of renewable energy as an overview for food processing sector. Here we will be focusing only on the use of solar energy for food processing and preservation. Now looking at the potential of solar energy in agriculture, out of the incoming solar energy, 51% of energy is being absorbed by land and oceans, and the rest is reflected back and radiated back to the atmosphere. Now the amount that is absorbed by ocean and land, this amount is a huge amount which can be explored very properly for different food processing applications. Now food processing applications can be performed by the application of heat or by the removal of heat. Now application of heat we can perform in terms of steam or hot water, and in terms of hot air also we can apply the heat. So when we deal with steam and hot water, the unit operations that are performed are blanching, pasteurization, sterilization, evaporation and distillation. Similarly, using hot air we can perform drying of food products, baking and roasting process. By removal of heat, the unit operations that can be performed are chilling, freezing, control and modified atmospheric storage. Some of the solar thermal applications in the food processing sector are, this is a greenhouse basically for greenhouse heating in University of Waterloo, Canada. This is a photograph that is being shown over here. Similarly, for drying of vegetables and crops, the wide variety of dryers are employed, and electricity generation for farming, for poultry farming basically, and in farming applications we can use the solar photovoltaics also in this regard. Solar energy utilization in food processing has a very wide application. The food manufacturing and storage are processes in the food industries with high energy consumption and high running time. The temperature requirement for food industry applications basically range from 60 degree centigrade to 180 degree centigrade. For example, food and beverage sector, they need a temperature range up to 180 degree centigrade. Drying and evaporation sector, they operate well in the temperature range from 40 to 130 degree centigrade. Cooking around 100 degree centigrade. Similarly, pasteurization of liquid foods, they need 65 to 100 degree centigrade. Cleaning of products and production facilities 60 to 90 degree centigrade, and blanching operation can performed between 65 to 95 degree centigrade. So, for performing these different processing operations in the food industry, these temperature ranges can be very effectively achieved by the use of solar energy. Solar energy can be broadly classified on the way how the output we are deriving from it. For example, direct conversion in terms of solar photovoltaics and solar thermal conversions by employing non-concentrating collectors and concentrators. Non-concentrating collectors are again classified into two types, flat plate collectors and evacuated tube collectors, whereas concentrators are again Fresnel type and parabolic type concentrators. So, first of all we will be discussing about the non-concentrating solar collectors, and the very widely used non-concentrating solar collector is the flat plate collectors. So, this is a schematic sketch of the flat plate collector. So, as can be seen, the flat plate collector basically consists of a flat absorbing metallic plate that is present at the bottom of this box. This is basically in the form of a rectangular box. The bottom plate is known as the absorber plate, which is normally made up of some metallic materials, which receives the short wavelength radiation directly and it is getting heated off. And on the top of this rectangular box we have a glass cover So, the short wavelength radiation basically falls on the glass cover, some portion of the radiation is reflected back to the atmosphere and the rest is transmitted through the glass cover and falls on the observer plate. So, the observer plate is getting heated off, and beneath the observer plate we can see there is thermal insulation provided at the bottom as well as the sides of the collector in order to prevent any heat loss. Tubes, channels or passages are attached to the observer plate to circulate the liquid required to remove thermal energy from the plate, because the plate is already black colored and it is heated off by receiving the solar radiation, and above this black color observer plate tubes or channels or you can see these passages are made so that the water should be circulated through these tubes and they receive the heat from the observer plate and they get heated off. Thermal insulation, as I have already mentioned, is provided at the back and sides of the observer plate to minimize the heat losses, and transparent cover on the top to reduce upward heat loss from the plate. So, whole of this system is encompassed inside a weather tight container in order to prevent it from adverse weather conditions, and these flat plate collectors are very effective for low temperature applications like drying of food products, sensitive food materials like tea leaves, coffee beans, and also for processing fruits, spices, cereals, vegetables and different types of fish and seafoods. Next type of non-concentrating solar collector is the evacuated tube collector. This evacuated tube collector basically consists of a series of transparent glass tubes, as can be seen from here. A number of glass tubes are present in a series and they are connected to a header pipe. Each tube consists, this is a sketch of an individual tube. So, each tube consists of a thick glass outer tube and a thinner glass inner tube. So, this is the outer tube and inside is a thinner tube. This is the. So, this thinner glass inner tube is covered with a special coating that absorbs solar energy, but inhibits the heat loss. Evacuated tube collectors do not heat the water directly within the tubes. Instead, air is removed or evacuated from the space between these two tubes. Between these two tubes, air is getting evacuated, forming a vacuum inside. This vacuum acts as an insulator, reducing any heat loss significantly to the surrounding atmosphere, making the collector much more efficient than flat plate collectors. However, these evacuated tube collectors are well suited to cold ambient temperatures and they work well in situations of low solar irradiance, providing more heat consistently throughout the year. But for process applications, we require the moderate temperature range for drying and blanching and other process applications where we can go for flat plate collectors. Now, coming to the heat transfer mechanism in a solar flat plate collector, this is the schematic sketch of a typical air heating solar collector, or basically it is known as a air heater. So, already we have seen the designing aspects of the flat plate collector. So, here instead of tubes we have the inlet air passage and on other side there will be the outlet passage of air. So, here we have this insulation provided and above that the black color paint is given. Above the insulation we have a metallic plate which is black painted in order to receive the maximum radiation, and air from one end to the other end is crossing the passage length of the collector and it gets heated off. So, this is the heat transfer parameters that are involved during the process of heat transfer in a flat plate solar collector. As can be seen, this black color is the observer plate which is painted in black. Beneath that we have this insulating materials and this is the glass cover at the top. So, radiation that is falling on the glass cover, a part of it is reflected back and the rest of the radiation is transmitted through the glass cover and absorbed by the observer plate. So, when air is passing from one end of the collector to the other end of the collector, it crosses the passage length of the collector. So, this observer plate is already heated off. Now, when this ambient air is passing above the collector, so there will be convective heat transfer from the plate to the moving air. So, this HCPA is the convective heat transfer coefficient between the observer plate and the moving air, which is a very important parameter to analyze the performance of the flat plate collectors. Similarly, other heat transfer coefficients also play a significant role during this heat transfer mechanism inside the collector. HRPC stands for radiative heat transfer from the plate to the cover glass. HCCA is the heat transfer coefficient from the cover glass to the moving air. So, these heat transfer coefficient are used for framing the energy balance equations and ultimately to calculate the overall heat loss from the collector. So, UB basically represents the bottom heat loss coefficient, UC is the cover glass heat loss coefficient, and there is of course a edge loss coefficient that is designated as UE. So, the total heat loss coefficient of the collector is designated as top heat loss coefficient, that is UC from the cover glass, plus UB bottom heat loss coefficient plus edge heat loss coefficient, and this UL is the overall heat loss coefficient of the collector, is a very important parameter to determine the performance of the collector. Now, this is some experimental analysis has been carried out, and the performance in terms of temperature variations at different locations of the collector has been shown over here. As can be seen, from morning 9:30 to afternoon 4 o'clock, the experiments were carried out in the flat plate collector. This is basically a no load experiment. So, for the collector at different locations of the collector, if you can see, we can place the thermocouples on the observer plate to measure the observer plate temperature, glass cover temperature. This is the air temperature, that is hot air temperature, that is air is passing from one end to the other end of the collector. This is the glass temperature, this is the mean plate temperature. In order to accurately measure the plate temperature at 3-4 different locations, we are placing the thermocouples to measure the mean plate temperature. So, these temperature variations along with the time of the day is being presented over here. As can be seen, the collector inlet and outlet temperature ranges between 39 to 50 degree centigrade for the inlet temperature, and for the outlet collector temperature lies in the range from 51 to 62 degree centigrade, and ambient temperature is in the range of 25 to 41 degree centigrade. So, the range between 51 to 62 degree is the hot air outlet temperature from the collector, that is basically used for performing any particular process application, and that is very suitable for different process applications in the food industries. And one of them is very importantly is the drying of food products, because drying basically needs low temperature application for sensitive food commodities, and that is what we are getting from these flat plate collectors. Similarly, the temperature of the observer plate, glass cover and radiation is also shown over here. We found that observer temperature is reaching around 82 degree centigrade, at the same time the glass temperature is 54 degree centigrade, and the radiation intensity maximum we can achieve from this is around 872 watt per meter square. To calculate the efficiency of a solar collector, in steady state condition, the rate of energy that is absorbed by the observer plate, because energy is being absorbed by the observer plate, and that energy, some portion of this energy is also lost, and the rest of that is used to perform any useful work. So, the rate of energy absorbed by observer plate per unit area can be given as Q observer is tau naught alpha naught I. Tau naught alpha naught represents basically, tau naught is the transmittivity of the glass cover, alpha naught is the absorptivity of the observer plate, and I is the solar radiation intensity. The rate of energy lost by the observer to the ambient per unit area per unit time can be designated as QL, which is represented as UL is the collector overall heat loss coefficient. As I have mentioned previously, it is the sum of top loss coefficient, bottom loss coefficient and edge loss coefficient. So, this is UL into Tp minus Ta. Tp stands for the absorber plate temperature and Ta stands for the ambient air temperature. So, the rate of energy absorbed by absorber per unit area is the rate of the useful energy plus rate of energy lost per unit area. So, Q absorber is nothing but equal to Qu plus Ql. So, the rate of useful energy is the requirement, which is nothing but equal to Q absorber minus Ql. So, from here efficiency can be found out as the useful energy per the incident solar radiation, that is nothing but equal to tau naught alpha naught minus UL is the collector overall heat loss coefficient into Tp minus Ta upon I. So, we will solve one problem based on this. So, calculate the useful heat gain and thermal efficiency of 1 meter square solar collector for the following design and kinematic parameters. Design parameters are given in terms of the product of absorptivity and transmittivity 0.8, UL is 6 watt per meter square degree centigrade, I is the solar radiation intensity 560 watt per meter square, air temperature, that is basically ambient air temperature, is 35 degree centigrade and absorber plate temperature is given as 75 degree centigrade. So, we are going to calculate what is the useful heat gain and what is the efficiency of the collector. So, first already the data has been given. So, we have to calculate what is the heat lost from the collector, that is QL. QL is nothing but equal to UL, that is the overall heat loss coefficient, into absorber plate temperature minus ambient air temperature, that is given already 75 and 35. So, we are getting the heat lost from the collector is 240 watt per meter square. Now, next useful heat gain is nothing but equal to the absorbed energy minus the heat lost from the collector, or energy absorbed by the collector minus heat lost from the collector, that is absorbed energy is nothing but equal to the product of absorptivity, transmittivity into solar radiation intensity. So, 0.8 into 560, that we are getting as 448 minus 240 is the QL, which we already got from here. So, we are getting 208 watt per meter square as the useful heat gain. Then we have to find out the thermal efficiency, that is Qu upon I. Qu already we have calculated 208 upon the intensity, that is 560 watt per meter square. So, we are getting 37.14% is the efficiency of the collector. Normally these flat plate collectors efficiency can go up to a maximum limit of 41% or 42%, but for getting higher efficiency we have to go for solar concentrators. Now, coming to the application of these flat plate collectors in the solar drying systems, and as we have discussed in the first module, again the solar drying system can be widely classified into different types. That means, it ranges from open sun drying to the solar dryers, and solar dryers basically we have already discussed it, the natural or passive solar dryers, forced convection solar dryers and hybrid solar dryers. These natural and forced convection solar dryers again can be classified into three common designs, that is direct, indirect and mixed mode type solar dryers, whereas the hybrid solar dryers are coming into picture because solar dryers have certain limitations, they cannot be used throughout the day and night. So, due to urgent need of the food processing industries for continuous operation of the different processes, so there is a huge demand of this hybrid solar dryer, where the processes can be applicable during the day as well as can be satisfied during the night hours by employing the hybrid solar drying technology. And hybrid solar dryers can again be classified as solar assisted drying systems and auxiliary energy source assisted hybrid solar dryer. When it is auxiliary energy source, this is in terms of thermal storage system, photovoltaic assisted solar dryers, DESIC and integrated hybrid solar dryers and biomass assisted hybrid solar dryer. And the performance evaluation of the solar dryer can be categorized into three important parameters: heat utilization factor, coefficient of performance and efficiency of the dryer or the drying efficiency. So, heat utilization factor is the ratio of the temperature decrease due to cooling of the air during drying to the temperature increase due to heating of the air. So, this is designated as HUF, that is heat utilized per heat supplied. That is basically the drop in dry bulb temperature of drying air upon the increase in dry bulb temperature of the ambient air, that is Tf minus Tc. Tf is the dry bulb temperature of heated air minus dry bulb temperature of the exhaust air, divided by dry bulb temperature of the heated air minus dry bulb temperature of the ambient air. And once we calculate this HUF, there is a correlation between HUF and the coefficient of performance. COP is the coefficient of performance, which is represented mathematically as Tc minus Ta upon Tf minus Ta. Now, drying efficiency basically it gives an effectiveness of the energy that is used for removing a particular amount of moisture from the food materials. So, efficiency during the drying process can be represented as the ratio between the product of mass of the water evaporated in kgs into the latent heat of water vaporization upon input energy, that is in the terms, that is solar radiation intensity into the cross sectional area of the collector in per time. So, this is the expression for calculating the drying efficiency during solar drying of food products. Next, another important application of the solar energy is in the preservation of milk and different juices, fruit juices. Basically, typical dairy plants derive about 70% of their energy requirements in the form of thermal energy, and the remaining 30% is consumed in the form of electricity. Pasteurization and sterilization are two important processes for preservation of the liquid foods. Flat plate solar collector, solar photovoltaic panels, concentrated collectors, evacuated tube solar collector can be used effectively to attain the pasteurization temperature. Beverages such as fruit juices, beer and wine, they can be pasteurized using solar pasteurization system for the shelf life extension. So, a schematic of the solar milk pasteurization system is shown over here. As can be seen, from the milk tank, the milk flows to a collector. This is basically a collector, and in this collector we have a number of pipes which are present in a serpentine manner. So, this collector contains a number of pipes through which milk is flowing from the milk tank from one end of the collector to the other end of the collector, and as per the principle of operation of the collector, the milk that is flowing through a serpentine manner inside the pipes is getting heated up by passing the passage length of the collector, and it is very clearly seen at different points valves are also provided to regulate the flow rate of the milk through the pipes. So, here during passing through the collector, the flow rate is maintained very accurately, so that sufficient time, exposure time will be given to the milk for getting the necessary heat. So, after coming out from the collector, if the pasteurization temperature is not reached or it is around 60 to 63 degree centigrade, then the milk is going to a holding tube where it can be kept for another 30 minutes and then it can be passed to the cooling unit. If the sufficient temperature has been reached from the collector outlet, then directly the milk can be passed to the cooling unit, from where the pasteurized milk can be collected. So, this is a typical example of the solar milk pasteurization system, which can be effectively used for different other liquid food products to get suitably pasteurized. Next, coming to the other application of the solar energy in cooking and baking processes. Solar cooking and solar baking process are again high energy consuming processes. So, here the employment of solar energy can play a very important role. Basically, these processes can be satisfied very effectively by employing the solar cookers or solar oven. So, solar cookers or solar oven, they are the devices which uses the energy of sunlight to heat food or drink to cook it or sterilize it by concentrating, capturing the solar energy and converting it to heat. The basic working principle is that it utilizes simple principles of reflection, absorption and the greenhouse effect to convert sunlight into heat. So, as can be seen, the box type solar cookers are easy to construct and very effective to provide the better quality cooked products also. So, here a schematic sketch of the box type cooker is shown, where the bottom of the box type cooker is black painted, again in order to receive the maximum solar radiation, on which the cook pot is being placed, inside which the food materials are present, and on the top we have a transparent cover or a plastic cover, transparent cover is provided so as to receive the radiation. Again reflectors are provided at the outside of this box so as to concentrate or to collect the maximum radiation and focus it onto a single focal point on this cook pot, so as the food materials can be cooked effectively. Similarly, this is a parabolic type reflector, where the temperature can be reached for a very high degree. For example, we can use this system for baking of food products, where the temperature ranges around 200 to 205 degrees centigrade, which is very effective for baking of food materials. So, here baking as well as frying also we can perform with this high temperature application, where these parabolic reflectors can focus the solar radiation at a single focal point, and that normally this cook pot is present somewhat at the middle of this parabolic reflector, so that it can receive the maximum radiation and effectively bake or fry the food materials during the process. So, advantages of this cooking and baking process are, they are relatively cheap, low technology devices, no fuel is needed. First of all, this is very important, we are going to reduce the fossil fuel use in this regard. Many non-profit organizations are promoting their use worldwide to help reduce fuel costs for low income people. They reduce air pollution and reduce slow deforestation and desertification that is caused by the use of firewood for cooking. So, these are some of the application of the solar energy that are very widely used for different unit operations of food processing industries. Thank you.